You should have two papers stapled together for this set of notes. It's the N3 notes. We are going to be discussing number sets in this video. As you can see, there are some definitions on the screen. You may want to stop the video if you're watching this at home and write these definitions in for complex numbers, real numbers, and irrational numbers. I will be giving you some examples of each of these as well as non-examples. The objectives of this lesson are that you can analyze the relationship between different number sets, and you can also categorize specific numbers into the appropriate number sets. So you should be sort of familiar, some of these things should be familiar to you from previous math classes. So the first set of numbers that we want to look at is the complex numbers. These are numbers in the form of a plus bi, where I is represented in place of a square root of a -1. And a and b here are real numbers. So some examples that we could come up with for complex numbers would be any number which includes a negative square root. So a negative number under a square root symbol. So we know that the square root of any number is going to be positive, but this is a situation where the number underneath the square root itself is a negative number. So that's what a complex number is. And non-examples would be things that are real numbers, because this I right here actually stands for imaginary. Okay, so a complex number is really an imaginary number and a real number mixed together. That's where we're getting this part right here. Moving on to the real numbers, I'd like to go over some examples. Real numbers are those numbers that are rational and irrational. So all rational and all irrational numbers. We will be defining those in just a moment. So some examples of real numbers: 2.7, 100, 0 is also a real number, pi is another real number, as well as -2/3. Okay, so any rational or irrational numbers. So the only things that would be non-examples of real numbers would be imaginary numbers, as we indicated just a second ago. Imaginary numbers are square roots of negative numbers. So for example, the square root of -2, that's an imaginary number. The square root of -4.7, that's an imaginary number. So just any square root of a negative number is going to be a non-example of a real number. And the definition of irrational numbers are any number that cannot be written as a fraction. Okay, so any number that cannot be written as a fraction using two integers. So for example, pi cannot be written as a fraction using two integers because it's a repeating decimal. And same thing with a square root of 2. Okay, there's no way for us to write that as a fraction. Also, a decimal like this that is repeating 2.75468, and then it just continues to go on and on and on and on and on. That would be an example of an irrational number. Some non-examples of irrational numbers are things that can be written as a fraction. So for the number 7, that can be written as a fraction because it could be written as 14/2. This decimal here can be written as a fraction. Remember, that's just 1/3. Okay, so the decimal 0.3 repeating is just 1/3, so that is a fraction. And then any number that looks like this that can be written as a fraction, and the number 0 also is a non-example because these numbers are not irrational. Next up we have rational numbers. These are any numbers that can be written as a fraction using two integers. They may be repeating or they may terminate. So in terms of some examples of rational numbers, the number 7 is rational. The number 0.3 repeating is rational. This decimal here, it is repeating, but it is rational because it can be written as a fraction, and 0. Some non-examples are going to be 4.7 over 5. That's a fraction that does not have two integers as its fraction. Pi is not rational. We just said that it was irrational, and it cannot be written with two integers. This number here, 2.75468, that just continues on with no particular repeating pattern, and it does not terminate, so it's, well, let's do this, dot, dot, dot. And then also the square root of 2 is not a rational number. It does not come out to anything that can be written as two integers as a fraction. Okay, moving on to integers. Any number in the infinite set of negative numbers, the number 0, and positive numbers. These are whole numbers. Okay, so any whole numbers, including the negative numbers, 0, and positive whole numbers as well. So some examples that we can come up with: 8 over 4. 8 over 4 is an integer because it's just 2. Negative 27. Remember, negative numbers are included in integers. And then a number that looks like this, 4 to the second power, is 16, and that is part of the integer set. So numbers that are not integers. Pi is not an integer. As we said, it cannot be written as a whole number, so that's basically what we're talking about, a number that is not a decimal. The number 2.5 is a non-example that does not fit in the set of integers, and neither does negative 4/3. Negative number fits, just not a fraction. So here, just want to remember that there are no decimals and no fractions, okay, in the set of integers. The set of whole numbers has any number in the infinite set of 0 and positive numbers. So there are no negative numbers in this set, and no decimals. So some examples of whole numbers. The number 0 is a whole number. Okay, again, just remember, 0 is part of integers. It's also part of whole numbers, but if you look real carefully down here at natural numbers, 0 is not in this set. Okay, so going back to whole numbers here, 0, the number negative 8 over negative 4, that's just a positive 2, so that fits in the set of whole numbers. Also, the cube root of 27, which happens to be 3, is also part of the set of whole numbers. So whole numbers are positive, and they are not decimals. And it includes 0 as well. Non-examples, negative 4 is not a whole number because it's got to be an integer. Okay, integers do have negative numbers in them. And 1/2 is not a whole number because it's a decimal, 0.5. And then, of course, 7.5. So you should be able to see a pattern. So with these examples, I should be able to ask you to give me an example of a certain kind of number, and you should be able to do that. Natural numbers are any number in the infinite set 1, 2, 3, 4. So basically, it's like the counting numbers, okay? Sometimes we think of these as the counting numbers. These are non-zero numbers. There are no decimals in this set. There are no fractions in this set. And there are no negatives in this set. Okay, so some examples here. We can have negative 6 over negative 2. Remember, that just results in a 3. The square root of 9, which also happens to be 3. The number 4 is part of the natural number set, and so is 3 to the third. That's 27. So some non-examples. 0 is not part of the natural number set. This negative value, negative 4. This decimal is not part of the natural number set. And a fraction like this is not part of the natural number set either. Please go ahead and turn your paper over. I'd like you to take a look at these two different diagrams that we have on the back. We have a classification chart that includes all of the different sets that we just defined and had examples of. So at the very top we have the complex number set. There is a special notation that people will see, you will see in textbooks and things like that. It's a capital letter C with this little line here. Okay, that's just a notation. So if you use that notation, that's indicating that you're talking about complex numbers. Real numbers are designated with this symbol here. Rational numbers are designated with a letter Q, but it kind of has this other little line in it, sort of like the C for the complex numbers. Everything has kind of a double line in it. Integer is going to be represented with a second line on the Z. Z represents the integer set. There is no special symbol for the whole numbers. Okay, so there's no special symbol for that one. The natural set of numbers is represented by a capital letter N with, again, another double line on it. And there is no special symbol for irrational numbers either. So if you see the capital letter C, you're talking about complex. Capital letter R, talking about real. Just wanted you to kind of picture all of these and how they kind of go together or don't go together. I'm also going to write some reminders of what types of numbers these are on the page here. So if you take a look now, I do have the examples written next to each type of number. So take a look again, review this page, add these examples to your notes as well, so that you can remember the different types of numbers that fit in each one of these different categories. With the Venn diagram that you see at the bottom of your page, we're going to show how each number relates and what type of number it is based on our definition. So all of the numbers in this set of numbers are going to be considered complex. Okay, and within the complex numbers there are real numbers. Those are rational and irrational numbers. So over here in this circle I'm going to write irrational. Those are the numbers that cannot be written as a fraction. And then we have rational numbers as well. Remember that real numbers are rational and irrational. But rational just means they can be written as a fraction. Irrational cannot be written as a fraction. Underneath rational we have integers, because integers can be written as fractions. Okay, integers include negative numbers and they include 0. They also include numbers that are positive but are not represented as fractions. They're represented as a whole number. Okay, and then with the integers, within the integers we have whole numbers. The only number in the integer set that's not a whole number is 0, and any negative numbers obviously don't. So these are all positive numbers. 0 is also part of that set. And then within the whole numbers we have a set called the natural numbers. And these are basically, if you think about it, these are just counting numbers, numbers that you would actually start counting with 1, 2, 3, 4, etc. So within those natural numbers we also have a couple of other categories which we didn't really define, but I'm going to be asking you about these as well. So we have composite numbers. Okay, composite numbers fit inside natural, and also within the natural numbers we have prime numbers. Okay, so prime, you remember, is a number that only has factors of 1 and itself. So composite is the opposite of prime. Composite is one kind of number that has 2 other factors other than itself. So for instance, 33 is a composite number because 3 times 11 make up 33. Prime numbers would be 13, 17, the number 2, etc. Things that don't have any factors other than itself and the number 1. If you can go to the last page of your notes, there are a couple of examples here that I'd like to go over. If you recall, one of our objectives is that you're going to be able to categorize specific numbers into the appropriate number sets. So we're going to do that right here with example number 1. So basically you're looking at the value, the number, and you're going to name all of the sets of numbers to which each number belongs. So the square root of 16, if you recall, is 4. It could also be -4. So which sets do 4 or -4 fall into? Well, if we're looking at just the positive square root here, we would have to say that it's part of the whole numbers, and remember that does not have a special symbol for it. And we could also say that it is part of the natural numbers. It is part of the integer set. It's also part of the set of rational numbers because it can be written as a fraction. And it's real, right? It's not complex, so it's real. And I think we have all of them. If we move on to part B, the number that we're looking at is -18. So we have to remember which sets do not include negative numbers. Whole numbers are not included here. There can't be any negative numbers there, and natural numbers cannot be. So basically we're going to say that it's all sets that do not include the negatives. So complex numbers would qualify here. Real numbers, because real numbers include negative numbers. Rational numbers, this number can be written as a fraction. And we also have the integers, but not any other sets. The integers do include negative numbers. For C, the fraction -7/8, we would have to say that these are, this particular number fits in the real number set, the rational number set, as well as the complex number set. It cannot fit inside the integer set because it's not an integer, it's a fraction. And obviously it can't fit into whole numbers or natural numbers because those don't include fractions either. So just those three. Now for part D, we have the square root of -7. If you were to plug this into your calculator to get a result, you would see that it's very irrational. All right, so you want to make sure that you write irrational for that one. That's one of the examples I've given a couple times now. And for E, we have a decimal number, which could be written as a fraction. So fractional numbers are the ones that we call rational. And rational numbers are also real numbers, so we have to go with real and rational. The number 0 fits into 5 different categories. It fits into the complex category, okay, the whole category, because 0 is part of the whole numbers, but it's not part of the natural numbers. It is part of the integer set, also real numbers, and rational numbers. It can be written as a fraction. Any number over 0 is 0. The final example that we have here on our notes today says, give an example of one number not already used in the activity or in the notes to satisfy the given conditions, if possible. Otherwise, I want you to write not possible. So for part A, it says, give a number that is real, that is rational, that is whole, that is an integer, and is a natural number. Well, if it's all of these things, we'd have to stick with which one? The final one here, because if you remember, if you go back to your Venn diagram, natural numbers are whole numbers are integers, integers are rational, and rational numbers are real. So we have to go to the base of our Venn diagram, or to the root of it, to find out what kind of number we want. So we want any natural number or any counting number. Remember, the natural numbers start at 1 and then they go up in a positive direction. So let's go ahead and have you give your own example over here on the side. Okay, I'm going to give you some hints, of course, but I want you to write your own example over to the right. Just a number that is a natural number, basically, here. Okay, how about if you look at your Venn diagram for part B, is it possible to give a number that is both rational and irrational? Looking at your Venn diagram, I hope that you can see the answer for that. If it is possible, go ahead and give an answer over here. If it's not possible, you can just write not possible. For part C, give a number that is real, that is rational, and that is an integer. Well, a number that is an integer is rational, and a number that is rational is real. So we have to give any example of an integer, and integers do include negative numbers. Okay, so any number, starting with any number that is negative, and then that goes up, and we do include 0 in the integer set. We do include positive whole numbers in the integer set, but no fractions. Alright, so give an example of an integer, because if it's an integer, then it's also rational and it's also real. For part D, a number that is not an integer and not irrational. So not irrational means that it is rational, but it is also not an integer. Okay, so it has to be then a fraction. Okay, and that would be part of the set of rational numbers. So it has to be rational. That's because it's not an integer, and we have to have something that is not irrational. Okay, so basically you're going to be giving me an example of a fraction that cannot be simplified into an integer. Can't be simplified into an integer. Alright, so think about that a little bit, and you have to remember what integers are in order to give the example of this. It would be a really good idea to review this. The activity that we're going to have that goes along with this really does force you to think about which set each number or each number type goes with.